Wait, how do you get up there? Yeah, Zoom's open. Ian, how do you get up there? Oh, okay. All right. Hey guys. So today we'll do Grover's algorithm. So last time we did Deutsch-Jones algorithm, which was like the introductory quantum algorithm. Now we'll be doing a new algorithm called Grover's algorithm. Its goal is pretty much to search for an element in a database in a quantum way, and we'll see the huh?
Last Wednesday.
Oh, 2 weeks ago then.
I mean, like, what was it?
Oh,
Like,
the
didn't hear what you
Deutsch-Jones
said.
algorithm? The Deutsch-Jones
Oh,
algorithm?
yeah, okay. I
Yeah.
didn't hear what you said.
Oh yeah. We'll do a recap of it as well. Yeah, we'll do a recap of it as well. But yeah, we'll be walking through the Grover's algorithm now. Again, just quick review, bits versus qubits. This is our state of our qubit. Some superposition of 0 and 1 with some weighted coefficients, and you have some probability to measure 0 and 1, as we've always done. And when you measure it, you destroy its state and you read out a classical outcome. Uh, when you have a multi-qubit system, you use the tensor product. So you can have four possible states with two qubits. And then again, you can arrange them in a column vector with four elements. And each element has a weighted coefficient. Entangled states, as we've said, is when uh, reading one outcome tells you something about the other outcome. So this is our canonical example of an entangled state where if you measure a zero on the first qubit, you know the second qubit's in a zero. If you measure the first qubit in a one, you know the second qubit's in a one. So something deterministic is said about the second qubit when you measure the first one, or vice versa. Um, our single qubit gates, our X gate flips between 0 and 1 state, represented in a circuit diagram like this. And then again, yeah, flips 1 to 0, 0 to 1. And then every gate has a matrix form, and you can think of applying the gate as doing matrix multiplication on the column vector of the input, and then you get some column vector as your output. Z gate, its operation is to leave 0 unchanged, and then multiply 1 by a -1 coefficient. This is its matrix form. And then again, remembering that these gates are linear. So if you apply it on a superposition of 0 and 1, you can kind of distribute the gate and then see how it acts on just the 0 and the 1. Questions on like the simple gates and stuff we've covered? Okay. Yeah, the H gate makes a superposition state. So if we take in a zero, we'll get a equally weighted superposition of 0 and 1, with 1 over root 2 as the coefficients. And then for 1, you'll get the same thing, but with the minus sign in the middle. Multi-qubit gates can act on two or more qubits. The one we look at is the main one we look at is the control gate, where it has a control qubit represented by the solid dot, and then a target qubit where the actual operation is. And then the gate will apply U onto the target if the control is in a one state. So if this is in a one state, it'll apply U to Y. Yeah. Questions on that? And then these gates create entanglement, as we've seen with the Joyce-Jones algorithm and stuff. Questions on that? Okay. Okay, now we'll recap on the algorithm we covered 2 weeks ago, which is the Joy-Jones algorithm. So now I'll start going a little slower. So the problem statement was that we have a function as our input to the algorithm. The function maps n-bit strings to single bits. So again, for example, you can have an n-bit bit string like this where n equals 7, and then you get some single bit like 1 or 0 as an output. It'll only be 1 or 0. Um, we're promised in the algorithm that F is either constant or balanced. We went over the definition of those. If F is constant, then no matter what you input into it, you'll get the same constant output. If it's balanced for exactly half the inputs, you'll get a zero, and for exactly half the outputs, you'll get a one. And then what we output in the algorithm is zero if F is constant and one if F is balanced. Questions on that? Okay. Um, Again, as an example we went through, is it this these are our functions outputs for these inputs, so is this one constant or balanced? Balanced. Yeah, balanced, because half the inputs are zero, half of them are one, or half the outputs, sorry. This one, constant or balanced, I'll just say it's constant because all the outputs are one no matter what you input. Everyone good? Hmm. Okay. Um, an important thing of the algorithm is that we don't know what f does. Like we don't have anything saying like f of x equals x, like an identity function or anything like that. All we can do is like chug inputs into f and then inspect the output, and then we have to determine something about f. So yeah, we call it a black box. So we have some input, we throw it into the function, and then we read f of x as an output without knowing what it actually is computing. Yeah, our classical solution was to just brute force it pretty much. So you start with all zeros, you input it into the function, you read some output, then you add a one at the end, so binary equivalent of one. You throw it in the oracle. We call it an oracle. So you just call F on it, and then you examine its output. If they match, then you keep going. And then you can just keep repeating. Let's say you keep reading zeros, and then you come to this input, which is exactly one more than half. So the 2 to the n minus 1 plus 1. That's the input that it is. And then if you read another zero from that, so you've read all zeros for more than half of the possible inputs, then you know immediately that f is constant. Because if it were to be balanced, then we know that exactly half of the inputs would be zero or one. Does that make sense? And then if we before we reach this 2 to the n minus 1 plus 1th string, if we read a 1 before that, we can say that f is balanced because uh these if it was constant, then we would get the same output. So these like contradict each other. Make sense? Um, oh, maybe. Right. All right. Questions on that classical solution for Deutsch-Lose? Okay. Sorry, I'll go a little fast. This one, hopefully it doesn't take too long, but yeah. The gist of it was that we have to make an exponential number of queries because in the worst case where we read the same number of input for one more than half of the list, we're calling 2 to the n minus 1 plus 1 queries. So that's an exponential amount of queries. With the quantum algorithm for Deutsch-Joseph, we found that we only used one query. Equivalently, we called the oracle once. So yeah, this is the oracle where we, instead of calling f as a function, we encode f's action and do some quantum gate to make it a valid quantum operation because we need our quantum gates to be reversible. You don't have to worry too much about that. But the way we do that is that it's a 2-qubit quantum gate. It'll take in one input X and then one input B. It'll keep X the exact same, and then it'll take B and then take f of X and then add them modulo 2. Or you can think of it as an exclusive OR. So yeah, this is the same as an XOR operation. So then this is the how we encode our function into a quantum gate. Does that make anyone questions on that? Okay. Yeah, we gave an example on how to encode a quantum oracle. So if we let n equals one, and then so then our function maps bits to bits. And then we said that f is an identity function, so it just takes an input, outputs the exact same thing. We showed that the four basis states map to these, and then we said that this is the exact same truth table as a C naught gate. And then so that means that our encoding of our oracle, which encodes our function, is just a C naught gate. Does that make everyone get that? On Zoom as well. I'm checking the chat if anyone has questions as well. Mhm. And then the important part of defining the oracle this way is that we showed the phase kickback lemma, which is where if we set this second register, this B register, to be the minus state in particular, we just chose that arbitrarily. It doesn't actually come from anything in particular. It just gives this very nice property that allows us to prove the correctness of the algorithm. We said that if we input X and then this minus state, we'll get oh well first we showed the yeah. Okay, yeah. This is the general thing. So if we input x and this minus state into the oracle, if f of x is 0, then we'll get the exact same thing back. If f of x equals 1, we'll get the exact same thing back with a minus sign in front of it. So then we generalize these two cases and say that uh, if you input x and then the minus state into the oracle, you'll get this coefficient with -1 to the f of x, and then the same exact thing back. So, and that's what we call the phase kickback lemma. And again, the minus state is what allowed us to do this and prove this. Anyone have questions on that? That's like an important part. Mhm. Good. Okay. Um, all right. So we proved the circuit for when n equals 1. So f maps bits to bits again. Um, we, I guess I'll just go over the idea that we went over. We basically applied Hadamard's to all of our qubits and then got into some superposition of qubits. And then we applied the unitary, or I mean, sorry, the oracle on this superposition of qubits. And and then when by linearity, it's like we distribute the oracle into each term of the superposition. So like um, oh, if we had like this isn't normalized, but if we had like some superposition of 0 and 1, and then we were to apply the oracle on it, then we could distribute the oracle into each term in the superposition because the gate is linear. And then by phase kickback, we had some encoded information about the function in this superposition state, final superposition state, and then we applied a Hadamard gate to undo it. That was like a high level thing. It sounds kind of like random, but it did we did show that it worked by tracing through the circuit last time. Yeah. So this was the circuit we gave. So we applied an H to get into superposition. We applied the oracle in superposition, and then we undid the superposition. And then these two gates turns the 0 state into a minus state. And then that we were able to do the phase kickback lemma because of that. And then at the end, we found that the state of our circuit is in the first qubit is a 0 if f is constant and a 1 if f is balanced. So then we can simply measure the first qubit, and then we're guaranteed to measure 0 if f is constant and 1 if f is balanced. Does that make sense at a high level, what we did? Yeah. We showed the example for just n equals 1, but again, the circuit generalizes. So if you have n qubits instead of 1, that's what this means. N qubits in the 0 state. Equivalently, you could draw the registers separately. You can do the same exact thing where you apply Hadamard's on each one of them. You apply the oracle in superposition, and then you apply Hadamard's again to undo the superposition. So yeah, it just generalizes. Um, okay. Questions on Deutsch-Jozsa and any of the recap stuff? Okay. Okay, so now we'll move on to Grover's algorithm. And last time I mentioned that the Deutsch-Joseph problem is kind of artificial, like it doesn't really have much of a use. But in this case, the Grover's algorithm does have a use, so we'll go through that. So the problem that Grover tries to solve is an unstructured search problem. So just like Deutsch-Joseph, we have a function as our input, and it'll take n bit strings and then it'll map them to single bits. Um, yeah, I say that here. Yeah, in some function f takes n bits, outputs 1 bit, and again, same example. You can, if n equals 7, you take some n bit string and you output 1 bit. Yeah. This time we're promised in the algorithm that there's one bit string that when you input into the function, you'll get a 1, but for every other input of n bit string, you'll get a 0. So it's basically like one of the inputs is like your target input that'll output 1 of when you put it into the function, and everything else is a 0. So you're searching for that x naught pretty much. Um, yeah, again. Yeah, there's some input that when that the function will return 1 on, and then for everything else it's a 0. And then I said that, but I already said that. But the output is that secret string where that output's 1. So it's like a marked input. Does that make sense? The problem that the algorithm's trying to solve? Yeah.
I mean, is it different than the Deutsch Joseph like algorithm and like what it's trying to find?
Yeah.
Yes. Okay.
So the problem with the Deutsch-Joseph algorithm, the output was just whether the function was constant or balanced. This time we want some specific input that outputs 1, right?
Okay.
So yeah, we were just solving a different problem. So it's like searching a database, for example.
Okay.
Yeah. Here's an example of n equals 3. These are your 8 possible inputs to the function. And then these are the corresponding outputs. So given this, what should the Grover's algorithm return? Yeah.
So 110.
Yeah.
Returns 1.
Yeah, exactly. So 110 returns 1, so we want to output 110. Yeah. Um, yeah. So let's first think about how we would solve this problem classically. So again, we know no structure about the data, so we can't use binary search if you know what that is. Huh?
It's linear, go through in order.
Yeah, exactly. So linear search is basically you start with all zeros, you input a function, you get a
Spelled
0.
classically wrong.
Huh?
You spelled classically.
Oh, sorry. So you start with n zeros, and then you input into the function, and then you get let's say you get a 0, then you try the next bit string, then you try the next bit string, you keep going, and then eventually you'll hit the secret string, and then you'll get a 1, and then you can just output it. Does that make sense? How we solve the problem classically? Okay, good. Yeah, linear search. And just like Deutsch shows up, this is an exponential solution. In the worst case, you go through everything. If the secret string is all ones, then if you start with 0 and then just increment, you're gonna go through everything before you find it. Yeah, so we say that this problem is the runtime of this problem is on the order of 2 to the n. And then this is our notation for it called big O notation. Grover's solution in the quantum algorithm will actually take square root of 2 to the n. So it's a polynomial speed up. The caveat is that it's not always guaranteed to succeed. With Deutsch-Joseph, we had 100% probability of succeeding. This time, that's not the case. So we have some probability of getting the wrong answer. And then we'll examine what the probability of this happening is. Okay, questions on Grover's problem? The problem we're trying to solve. Okay. Okay, before we start, we're just going to define some notation that we'll use throughout the entire algorithmic analysis. So we're going to define this vector A, which is a superposition of all the strings that will return 1 when you input them in the function. However, in this version of Grover's problem, we said that there's only one, which we called x naught. So this A is actually equal to x naught. So I think I give an example of this. Yeah.
How would you apply this algorithm to like actually searching for like an element in a collection or something?
I mean, it's pretty much like that. It's like if you're searching for something, it's like you can turn on a function if you have that secret input. Yeah. And then yeah, and then B will be the exact same thing, but for all the uh elements out of n bit strings that return a zero when you input them into the function. In this case, those are the other 2 to the n minus 1 bit strings. So it'll have 2 to the n minus 1 bit strings in it. And then we're gonna do an equal superposition of them, which means that we weight them all the same, which is that coefficient. And then this notation just means we're adding all the vectors in that set. So we're letting B be that set of like vectors that or of bit strings that return zero. I give an example of this, I'm pretty sure. Yeah. So if n equals 3, you have 2 to the 3, which is 8 possible bit inputs of the function. Let's say that 101 returns 1, which is the one we want to solve. And then for all the other inputs, we output 0. Then this A vector is just that 101. And then this B is just all the other 7 inputs, all weighted equally. Does that make sense? Okay. Okay. Yeah. So given that uh those vectors, we're gonna do something special that we'll go over. But first, we're gonna go over what a basis is in a general classical like vector space, like the real numbers. So let's just say you have a 2D plane and you have some vector, let's say we say 2, 3. So it's some vector that's 2 steps in the x direction and 3 steps in the y direction. This vector is represent what we call the standard basis, where we just use 1 unit of x and 1 unit of y. But we can express this vector in any arbitrary basis. So if we defined our basis as 1.5 in the x direction and 1 in the y direction, so this red arrow right here, and then the second basis vector as -1 in the x direction and -1 in the y direction, then we can express this vector as the same of a sum of those two. So we take 2 of these red ones, which is 2 of this basis vector, and then 1 of the second basis vector. And then if you add them like tip to tail, you can see that we get the final point. So it's the exact same thing you do here, except it's in a less obvious basis. Yeah,
But if you go to the second picture,
yeah.
the blue vector is not minus x hat plus minus y hat.
So it is, but it's not like centered at the origin. So
No, it goes,
oh
it should be positive.
yeah, it should be positive y hat. Yeah, okay, yeah. Positive y hat, sorry.
So
Yeah, yeah. The basis is the second basis is negative minus x hat plus y hat.
doesn't work out. Let's go.
Yeah. All right, thanks. And also if you distribute this 2 into like here, then you like combine like terms and simplify, you'll end up getting the same exact thing. But yeah, the point is we're saying that we can redefine what our scale of our basis is. Is that like clear to everyone? Okay. So so those A and B's that we said before, which are the good and bad, or I called them awesome because it's A and then B for bad. It turns out that when like the state of our algorithm, we want to express it in this basis by A and B. So like intuitively, it should make sense because we want to see how close we are to having an quote unquote awesome vector and how far away we are from having a quote unquote bad vector. We'll formalize that later. But here's a quick example. So let's say you have n equals 3 again, so 3-bit strings, and you have some linear combination of the 8 basis states. You can instead express that in this basis spanned by this A and B with some new coefficients, capital C1, capital C2. And again, if we use the same example we did last, or actually, no, I don't do that here, but A is that secret vector that we want, secret bit string, and then B is some weighted combination of the bit strings that we don't want. Yeah, here's an example again. So same example as last time, n equals 3, and then the secret string is 101. So if we have some random vector, I just made this up, that's this combination of the 8 basis states, then we can equivalently express that as 1/2 times the A basis vector, which is right here. And then with this coefficient, √3/2 times this, which is the second basis vector, just B. So that contains all these terms. So it's just some different expression of the same vector in a different basis. But you can see that this here is actually 8-dimensional. And it's like we've kind of switched down 6 dimensions into like this B vector. So now this is now 2-dimensional. And that'll actually give us a nice geometric picture when we analyze Grover's algorithm. So we'll be doing that a lot. Questions on that? That's like a fundamental thing. So mm, mm, mm. Okay. You can stop me at any time if you have questions. Oh, okay. This is the same exact example. We have this state. I just computed the sums, so you end up getting zero point 0.5 times this A, and then 0.866 times this B. And then again, since this is now 2-dimensional space, you can express this in like a 2-dimensional plane. So this is weighted okay, so I note this here. We actually, this is just like standard convention that we put the B one first on the x-axis and then we put the A one on the y-axis. So this is √3/2 in the B direction and then 1/2 in the y direction or in the A direction. So yeah, this green vector is our state in this basis spanned by A and B. Yeah, and then the convention is here. Does make sense? Okay. Um, yeah, again, it should hopefully make some intuitive sense why we're doing this. So when we're trying to prove that our algorithm is correct, we kind of want to see how close our vector is to the A axis, and then that'll give us a higher probability of measuring a like a right solution. As you can see here, like the more, if you like project this vector onto the A axis, the bigger that this component is, the higher probability you have to measuring like a good state at the end. So yeah, we'll formalize that as we go. But yeah, make sense? Yeah. Yeah. And again, if you write your state as a combination of uh, as a combination of these A and B vectors, then the probability of measure of like solving the problem successfully is just the coefficient of the A squared. So that's why we kind of rewrite the vector in this basis. It's like we can literally like read off the probability of solving the problem correctly. Questions on that? Yeah. And then again, probability of failing would be the coefficient of the B squared. Okay. Um, yeah. So we'll start the algorithm with n equals 2, and then we'll examine how we're doing it. So with Deutsch-Jose, I kind of like gave you the circuit and then we worked through it. Now we'll kind of like reason why we're doing what we're doing to solve the problem. So hopefully it should make more sense. So n equals 2, so we have 4 possible inputs. Let's say the secret input is 0, 1, so that returns 1 and everything else returns 0. Again, so we want to output 0, 1 at the end. We can define our A and B. Our A will just be that 0, 1, and then B will be an equal combination of the other 3 states. Good? Okay. Yeah. Again, like Deutsch-Jose, we're going to start with 0. That's like the easiest to prepare. So we're just going to start with 0, 0. And again, like Deutsch-Jose, we're going to apply a layer of Hadamard gates to get into a superposition. That's like a general thing in these algorithms. Like you almost always want to apply Hadamard gates to get into a superposition. First thing you do. Yeah. So the state becomes H tensor H on the 0, 0 state. Uh, H on 1, 0 gets you this combination of 0, 1. H on the second 0 gets you this same combination of 0, 1. Combine the tensor products, you get an equal combination of 0, 0, 0, 1, 1, 0, and 1, 1, all weighted by 1/2. So yeah, good. And then again, we want to do this rewriting thing where we write it in terms of A and B. So we know that A is 0, 1, so it's going to have a coefficient of 1/2. And then B is 1/√3 times the other 3 vectors added. And then the coefficient of the B will be √3/2. Make sense? So we're rewriting our whatever state we are in the algorithm in terms of these A and B vectors, basis vectors. And then I show this we'll show this geometrically. We'll be showing the geometric picture a lot because it does help. So after we apply Hadamard gates, we're now at this point in this 2D space. So we're some vector at some point. If we measured the state directly, we already have some probability of solving the problem, but it's very low. So we want to increase our probability of solving the problem by getting this vector closer to the a-axis. Does that make sense? Why we're kind of rewriting it in this basis? So yeah. We're gonna look at the angle relative to the b-axis. So in this case, it's just the inverse tangent of the opposite angle, which is the 1/2 over the adjacent angle, which is √3/2, which is pi over 6, 30 degrees. Ideally, we want our vector to be very close to the a-axis to solve the problem. So this theta angle is gonna approach pi over 2 degrees, which is 90, pi over 2 radians, which is 90 degrees. I think I also say that. Yeah. Ideally, theta equals pi over 2. Then if we measure, we have a 100% probability of solving the problem. Usually that's not the case, though. Yeah. Make sense? Questions? Yeah, like we said, per iteration of the algorithm, we're gonna apply some series of known reflections to basically boost this angle to get as close to the a-axis as we can. We can't rotate it arbitrarily. We can only do things out like because we don't actually know where the state is. We just have to reason where the state is and then measure it at the end. So we'll go over how we're gonna do that. So let's say you're given some vector in this space and you want to somehow get it closer to the a-axis, but all you can do is reflect about this a-axis, the b-axis, or the psi-axis. That's all you know. So just like forgetting about all the quantum, like, does anyone have any idea of how you would do this? And the hint is that you would need to reflect two things, about two things in a specific sequence.
Reflect about B and then reflect about original psi.
You said B and then psi. Okay, yeah, that's correct. Yeah. So I'll go through that. Yeah. You first reflect around the B axis and then you reflect around psi. So if you start in this state, which is what we had before, you reflect around B. If you are at original angle theta from the B axis, you reflect. Now you're at theta on the other side of the B axis. Make sense? Simple reflection. Then if you take that vector and reflect it around this original psi axis, if you're originally 2 theta away from the psi axis, and then you reflect it around the psi axis, you're going to be 2 theta away from the psi axis after that. So now your state, after you do these reflections, is much closer to the a-axis by 2 theta. It's closer by 2 theta. Does that make sense? Good. Okay. Yeah. So the original angle with respect to the axis went from yeah. I think you're pent. Wait, maybe. Huh? Oh, okay, yeah. No. I wasn't on the eraser before. Anyway, so the angle of this vector original was at theta. The angle of the new vector is 3 theta. So we increase by 2 theta. Good on those two reflections. Those two reflections are literally what we do in the algorithm. We just reflect around B and then we reflect around psi. That's like, and we just keep doing that, right? So like it looks like we're already very close to A, but this is for the n equals 2 case. If we were to do this with a very high n, we're gonna have to repeat it a lot more times. We'll go over that. Yeah, again, we increase the angle by 2 theta. And yeah, that means we have a larger probability of measuring an awesome result because the projection of this vector onto this a-axis is more. Yeah, again, essence of Grover's algorithm. We just keep reflecting around B and then reflect around phi or psi. And then every time we do that, we just keep increasing by 2 theta each time we do that. Yeah. Okay. first goal after you apply those Hadamard gates is to reflect around B. That's the first thing we said we should do. So you have some state weighted by C or by B and A basis vectors, and we want to reflect around the B axis. So now our question is, how would we do that? This is the gate that ends up allowing us to do that. We call it ZF. This actually is our oracle because it has F in it, so we have kind of F in the X or in the subscript there. So it's a 1 qubit gate, although it does use in the actual implementation, it'll use like in a helper qubit, but all it does is add a coefficient in front of the input state and then just add this -1 to the f of x term. And then we'll go over why this actually reflects around the b-axis. So yeah, again, remember, if you're in a good state, or I keep saying good, if you're in an awesome state, then your f of x will return 1. So let's just say x is awesome. Then f of x is 1, which means that -1 to the f of x is -1. So if you're in an awesome state, you'll add a -1 coefficient. If you're in a bad state, then this f of x will be 0. And then -1 to the f of x will be a 1, so it'll do nothing. So yeah, again, if you have some vector A, or if you have some qubit A, state A in your awesome states, if you apply the ZF, you'll get -A. If you have a bad state and then you apply ZF, you'll get the same thing back. So yeah, you basically mark the awesome states with like a -1 coefficient. Yeah. So again, if we're inputting this state in our vector space of A and B, capital A, capital B, we apply ZF on it. It'll take all the awesome states, it'll mark them with the -1, like all of them. So this actually is a reflection around B. And then here's a geometric picture. If you have this vector, which is the one we've been using, you apply this ZF and it does nothing to the B states, but then it marks the awesome states with a -1. Now it's on the other side of the B axis. So we've done that reflection. Make sense? I'll pause for a bit just so that's clear. I'll go back up here as well. Yeah. So this single gate will reflect around B. Okay. Um, okay. Here's an example worked out again. Our previous state, we had, or actually, no, this is actually the same state as this. Um, it's using our example before where 0, 1 is A, and then B is this combination of the other ones. You apply ZF and you okay, first I'll work out on the computational basis. So you take this after applying Hadamard gates, you apply ZF on it, it'll add -1 to the f of 0, 0 in front of the 0, 0 state, and then -1 to f of 0, 1 in front of the 0, 1 state, etc. We know that this is the only one that equals 1 because this is the secret string. That's just how we set our problem up. So all of these ones will all go to 0. This is the only one that'll go to -1. So we've marked our 0, 1 state with a -1 coefficient. Does it make sense? Then if we translate that back to our A and B basis, this is just keeping B the same, but then now A has a -1 coefficient in front, because if you distribute this A to here, you'll get the 1/2 there. This is -1/2 A. Make sense? Okay. Uh, okay. Yeah. Again, ZF is our oracle. It does something about F. So yeah. What do I say here? Yeah. So we've encoded F into our oracle somewhere, which our encoding was doing that -1 to the f of x. This is a call to F. So we've encoded F into our oracle. Yeah. Okay, so just another encoding of ZF, for example. So let's say, how do we actually implement ZF? We know what it does. How do we actually implement it? Here's our example that we've been using. 0, 1 is 1. Everything else is 0. We can encode our oracle like by this circuit. So what this does is it uses a helper qubit initialized in 0, and then these are two input qubits. So what do we want to do? We want to, let's say these two input qubits are in 0, 1, and then in the output, they should be in negative 0, 1. If they're any other state, it shouldn't do anything. So what we do is we apply this double controlled C naught gate, except the first qubit is this open dot, which is an anti-control, which basically means that if it's in 0, then it'll trigger the control condition. If it's in a 1, it won't trigger the control condition. This is our regular control. Sorry, anti and combined, it'll only apply X onto this helper qubit if this original state is in 0, 1. So this first qubit's in a 0, it'll trigger the first one. If the second qubit's in the 1, it'll trigger the second condition. And then if both of those are true, it'll apply X on the helper qubit. And then if it applies X on the helper qubit, it'll be in a 1 state. If it doesn't if it's not triggered by both the qubits, then it'll be 0 still. Then we apply a Z gate. Let's say this is a Z, let's say this is in 1, so we input the right state. If we apply Z, it'll be a negative 1. And then now the combined state of the 3 is 0, 1, and then tensored with negative 1 by this point right here. And then this coefficient can just be carried over. So it can just be negative 0, 1, tensor 1. And then this one's our helper. And then this red box right here is an uncompute. It basically says that we should leave the ancilla or the helper qubit in the same state we started it as, so that we can reuse it for something else. So we just apply the same exact gate that we did before, and then it'll flip this ancilla back to a 0. So we get the same exact first two qubit state, tensor 0. And then now if we input the right things, we now added the negative 1 coefficient because of this Z gate that does that to the 1 state. So that's how we encode that's an example of how we would encode our oracle. Does that make sense? Questions on that? Okay. Again, this is our ZF encoding, and that's our oracle, and that'll reflect around the B axis. What is this? Oh, I just proved that it's right, although I have already done that. Um, let's say this is our same encoding. Let's say you input 0, 0, and then the helper qubit's in 0. After you apply this C naught that's anti-controlled by the first qubit and controlled by the second qubit, what state would you get?
The same.
Yeah. Yeah, the same thing because the control condition wasn't hit, that the first qubit's in 0, and then the second qubit's in 1. And then after you apply the uh, identity on the first two qubits and then a Z on the helper qubit, what would you get? So this one gets an I applied to it, this one gets an I, and then this one gets a Z.
Same.
Yeah, the same thing because Z doesn't change 0, it only changes 1. And then likewise, when you apply the last one, which is the exact same thing, you don't hit the control condition, you get the exact same state back. So if you just look at the first two qubits, you've done what you needed to do with the oracle. You haven't changed anything. If you apply 0, 1, uh which is our good state, awesome state, whatever. You, I went through this. You hit the control condition here. So you do change the helper qubit to a negative 1 or to a 1. You apply Z on the helper qubit. You get this negative 1 factor that you can carry over here. And then you uncompute the ancilla of the helper qubit by applying the same gate. It'll turn that 1 into a 0. our input state was 0, 1, our output state is negative 0, 1. We've added the negative sign. And then with the last two states, we don't change anything. It's the same thing. None of the control conditions are hit. So that's how we would encode our oracle. Yeah. Yeah. So far we've in the algorithm we've applied Hadamard layer to get a uniform superposition, and then we've done a reflection along the b-axis by applying this oracle ZF. So just as a circuit, you apply H's, you apply ZF. That's it. Yeah. Next thing we said we need to do is apply reflection along the psi axis, which will boost our angle by 2 theta, as we said. So questions on the first part before we continue? Tell me if I'm going over time as well. I know we're kind of low on time, but anyway. Video. Yeah, are you guys following? Good. Okay.
Yes, I know why.
All right. So next step is to reflect along psi. Um, Again, this side that we're reflecting upon around is a uniform superposition. It's what we got from just applying Hadamard gates to the 0 state. So that's what this solid is right here. So we need to reflect around that. I think I just give you the thing, yeah. So the matrix representation of the gate that'll reflect around psi is given by this, which has a little weird notation. So I go through an example. So let's just say n equals 2 again. Psi is 2 Hadamards applied on both qubits of the 0 state. In matrix form, you get first you get uniform superposition. In matrix form, it's this column vector. And then if you do this ZF, that weird formula I gave, you do 2, and then this psi that we just set up here, and then we take the transpose of that, which we call the bra. Then you can do matrix multiplication, and then you subtract the identity, you get this. So it's a matrix. So you get a matrix form, and then remember gates are matrices that apply on vectors, which are our states. So this is what a matrix form would be like, for example, for n equals 2. Um, yeah. Let's prove that this is right real quick, because I kind of just like threw it at you guys. Yes.
Is it just that in general where you just put psi where the halves are?
Uh,
Like if psi is not a half, a half, a half, a half.
well, in general, it's going to be like 1 over root 2 to the n, like this stuff right here. And when n equals 2, it happens to be 1/2.
Okay.
Yeah, because, well, if n equals 1, we got 1 over root 2 is 0 plus 1. And then n equals 2, we get this state. And then if n equals 3, you get 1 over this. And then you add up all the 8 basis vectors and whatnot. Yeah. Okay, so let's show that this is right. So let's say you have some vector in that same space with A and B, you want to flip it around the psi axis. So we're gonna do a similar basis argument where we express the vector instead of terms of A and B, we're gonna express it in terms of psi and then a vector perpendicular to psi. So if our vector is this purple one here, it has some component that's parallel to psi and it has some component that's perpendicular to psi. That's just weighted by these alpha betas. You just add them, you get the same vector, right? So instead of doing this component along B and then this component along A, we're just expressing it differently. Just a change of basis. Good on that. Um, yeah. And then the fact that we're going to leverage is that these vectors that are psi and psi perp are or orthonormal, which means if you take the inner product of them with themselves, you'll get 1. If you take the inner product of them with each other, you'll get a 0. Yeah, it's like taking the dot product of vectors pretty much. Um, yeah, so now let's just take that state that we made, this state right here, and then apply the reflection. So this is our state, this is our proposed reflection. Do a little distributing. This 2 ket psi bra psi goes into this A ket psi. You get this term. And then you do that, you just FOIL the terms. And then we said they're orthonormal, so this psi dot psi will get you a 1, and then this psi dot psi perp will get you a 0. So this whole term will go away, and then this term will just multiply out to be 1. And then down here, yeah, I forgot to say you just get identities on these that come from right here when you FOIL. You do that, you get this state. When you bring this to a 1 and then this to a 0, it shakes out that whole term. And then these two terms are common, so just subtract them. You get alpha psi minus beta psi perp. Compare that to the original one. You've added a minus sign in front of the psi perp component, which means that's a reflection around psi. Here's the geometric picture. If you start with our original state, and then you do the same thing, you add a negative sign in front of B, you've now reflected it because this B component now goes the other way. And then the alpha component stays the same. So I went kind of fast through that, but does that make sense? Basically, we just showed what operator does a reflection around the psi axis. Okay. Um, I just gave you the matrix form or what you can expand to be the matrix form so we can put it into actual gates. Let's do some algebra on it and then we'll see what gates we have. So we start with this. Um, what we're gonna do, we know that psi is the application of Hadamard gates onto the all zero state, so we can just sub that in here. And then here we can do the same thing, except we take the transpose of it, but the rule is we swap the order of them. So this we get a bra like n bra zeros, and then again this h. Does that make sense? Like how I subbed in psi, and then like it's transpose, or what we call like good. Right. Um, and then this, we did nothing to here except just move the 2 in here. This identity is exactly equivalent to Hadamard n times the identity times another Hadamard n times because of the fact that when you apply Hadamard and two Hadamards, you get the identity. So you can see if you were apply identity on this H, you would just get an H, and then you apply this on this, and then you get another identity. Good. So it's just expressing the identity in another way. Now we can see that both of these terms have n Hadamards in front and n Hadamards in the end. So we can factor those out. So we take this inner component and then subtract the identity right here, and then factor out the Hadamards. Is that good? Just taking those out. Okay. And then this term in the middle, we call Z naught, which is another gate that we use to do the reflection. Um, in form, it looks very similar to this, where you have 2 and then some outer product, we say, of some state and then minus identity. So what it actually, so if this is a reflection around psi, oh, if this is a reflection around psi, this is a reflection around this 0 to the n. It's not like too important, but like that helps us express z in like a in this form down here. That if z is all zeros, it'll apply a negative sign onto it. If it's not all zeros, it'll do nothing. That's literally all it does. But this is just like the more like complex form of it. Questions on that? Sorry if I'm going fast. I know we just have time limits. Good. Um, Okay. We showed how to implement ZF. Now we can implement Z naught. Note that ZF is the oracle, Z naught isn't, because Z naught has nothing to do with F. It's completely independent of F. Like it'll be the same in no matter what implementation of Grover's algorithm you do. So but it looks very similar to ZF because remember ZF would apply a negative sign if the input state was whatever the secret string is. Here, the quote unquote secret string is just all zeros. So we're just applying Z if the input state is all zeros. And that's more explicit here. If all of the n input qubits are 0, which is what those n anti-controls mean, we'll apply an X8 on the helper qubit, then we'll apply Z, and then we'll do an uncompute, just like we did with ZF. And then you can trace through this. It basically says that because of these anti-controls, it's like each of those n qubits has to, like main qubits has to be in the zero state to flip the ancilla into a one before we apply Z. And then the Z will apply -1 if it's in a one state, and then do nothing otherwise. So that's just an implementation of Z0. Make sense in general? Not the terribly most important part, mostly just like proving the stuff that we're using that it works and kind of giving intuition on why we're doing it. But the big picture here is that we're reflecting around the psi axis to get closer to that A to measure an awesome state. Yeah, here I say the same exact thing. So here's the big picture. You have some vector in the space span by A and B, and then we rotate it counterclockwise by 2 theta. We first reflect it around the B axis by applying this ZF oracle. Then we reflect it around the psi axis by applying this, which is H and H Hadamard gates, then the Z naught that we just defined, and then another N Hadamard gates. All we've basically shown in the last few slides is that this is correct and this does that flip. Um, if you didn't understand it, you can just believe me, I guess. Um, and this is what we call the Grover iterate. It'll basically perform this 2 theta rotation. It'll first apply ZF and then apply this reflection around psi. So if you start some psi, you apply this G Grover iterate, you'll increase the angle by 2 theta. And that'll get you closer to A for most vectors, I guess. Yeah. Makes sense in big picture now. Questions in Zoom? Okay. Yeah. Again, increases our probability of measuring an awesome state. Yeah. So the first thing we did in the algorithm was we applied a layer of Hadamard gates. That'll get you to some angle theta. And then you apply K Grover iterates. Each Grover iterate increases your angle by 2 theta. So then your final angle ends up becoming this 2K plus 1 times all times theta. Just because you increase by 2 theta each time. Good. That's just that's why this geometric picture of A and B in like a specific space really helps because you can see like, oh, you're increasing by 2 theta each time. Yeah. In circuit form, let's just say n equals 2. You apply a Grover iterate. It looks like this. So first you apply layer of Hadamard gates. You apply 1 Grover iterate, and then you're increased by 2 theta in that space. We just analyze that, and you just keep applying G's to get closer to the A-axis. So obviously something you might want to ask is like how many Grover iterates do you actually need to apply to like have the maximum probability of solving Grover's problem. So, and also before we do that, like each Grover iterate just has one ZF. We said ZF is the oracle. ZF calls F once, and so each Grover iterate only calls F once. So remember the classical solution, we had to call F exponentially many times, possibly 2 to the n times. Okay, I said I'm just predicting myself. Yeah, classical solution, order of 2 to the n calls. Yeah. And then we said a while ago that to have the best probability of measuring an that's awesome state at the end, we want our theta to be 2 pi over 2 radians. That means we're perfectly aligned with the a-axis. So theta equals pi over 2. That'll give us a 100% probability of solving the problem. Ideal case, not always possible, almost never possible. But yeah. We just said that we apply K Grover iterates and we change the angle to 2K plus 1 theta. So all we have to do is just solve the problem. All we have to do is just solve the equation for K. The angle after K Grover after K Grover iterates, and we want it to be equal to pi over 2. Let's just solve for K. Distribute the theta, subtract this theta on this side, and then divide by 2 theta. And this is our expression. Not very helpful right now because it's in terms of theta. We want it to be in terms of n because the way we analyze how good our solution is how many times we call the oracle in terms of n. So yeah, again, to compare it to the exponential amount of classical calls, we express in terms of n. So let's just do some trigonometry real quick. Um, if we start with, so theta, remember, is our initial angle when we first apply a layer of Hadamard gates. So it'll just be some uniform superposition. So if we just, this is our example for n equals 2 that we've been using. If we just generalize that, our state will look like this, where the b component is this large 2 to the n minus 1, all square root over n, and then this, the a component is just 1 over n. So it's like, if you just plug in n equals 2 into like all these, you'll get like this right here. Yeah. So in reality, obviously the theta is not this large. Like if n is really huge, like it's literally going to be like almost parallel with the z-axis, right? As n increases, 1 over n decreases. So it's going to get very close to the b-axis. We just now we just need to solve for the angle. So the tangent of this angle is this component over this component, which simplify, you get 1 over root 2 to the n minus 1. And now we're just going to make a approximation. When n is large, then this minus 1 is pretty insignificant. We'll just approximate as to the n. And also when n is large, this theta angle is small by what I was just saying before. If n is large, you're like very close to the b-axis, so this theta gets really small. When theta is really small, we can approximate tangent theta as approximately theta. If you remember the graph of tangent, it's like all these asymptotes, and then like this is x equals 0. So it almost looks like this linear graph at the origin. So that's called the small angle approximation. You can also approximate sine theta as theta, but tangent is sine over cosine, so it's like, and then cosine looks like 1. Anyways, so we approximate theta as 1 over root 2 to the n. And then this is our expression before. We can just plug in theta equals 1 over root 2 to the n. And then simplify, do some algebra. And then this 1/2 is pretty insignificant. This is our approximate value of how many Grover iterates we need to apply. And this is, oh man, it is not, it is, it speeds up, I promise. This is order of root 2 to the n. Yeah, this is, if you just look at the highest like power in there, it's root 2 to the n. This constant is kind of irrelevant. Yeah, so it's a speed up. Now we said before that it's root 2 to the n, that's how you get that value. Okay, that's Grover's algorithm. So sorry I went fast at the end, but I also had 3 blue, 1 brown. If whoever knows has a video on this, I wanted to show. It does help. I mean, it's basically what we showed, but it's we can cut it early, but are there questions before that?
Explain the fact, however, like in 50 sentences, like the three ways.
I guess, yeah. I mean, I watched this video before.
Okay, okay, good.
Or well, I only like something.
Mhm.
But essentially, so like search for the like key, you're going to basically the one bit string that is the key that will return 0, or will return 1. You're gonna make it, at least how the video explains it, you like make it negative, which I think is, I'm assuming is flipping it on the bad
Yes,
axis.
yeah.
Is the same as making the key negative.
Yes, yeah, exactly.
And then once you do that, then you said that there's a way, now that the key is negative and all the other bad things are positive, there's a way to shrink all the other bad things and then increase the key, which is what we talked about, where
That's the second
you
reflection.
flip over the
Yeah.
y-axis. And then you kind of just keep repeating that until you get a high enough probability that you will.
Exactly, yeah. And then, yeah, we just showed that the amount of times you should repeat it is on the order of root 2 to the n. And then each call calls the function once. So yeah, that's how many times we call it. Okay, let me figure out how to like do this video. Um, Let me stop this. Then this. Wait, Ian, do I have any slides on here?
Um,
I should have set that up before.
No, it's
Uh, huh?
I'm just listening.
Uh, can you pull them up real quick on your iPad? Because I just need the link.
Yeah.
Oh wait, no, I got it. Oh, you don't have YouTube installed.
I don't.
Yeah. Go back to notability, I guess.
I think we'll skip the video for now. I mean, think it's small.
Want to skip it?
Yeah.
You guys want to watch the video?
I would.
It's just a small, it's like a small snippet. We can also end it in the middle. Whatever you guys want. You want to watch it? Okay.
It's not technical.
No, it's basically what I said, but just using his nice animations. Fine, okay, fine. I think this will be on for recording. Oh.